Hello, this is Mr. White, and this video is about the sum and difference trigonometric identities. So, this is the list of what our book calls the fundamental identities. This should be very familiar to you now. I've had it in previous videos, we've gone over it in class, and I've made the claim that all of these need to just look obvious to you. You need to have the right mental picture in mind such that none of these should be a surprise at all. You shouldn't feel like you're memorizing any of these. I'm not going to make any such claim with the sum and difference identities. I'll go over the proof of where these, or at least one way where these formulas came from in class. I'm not going to go over that here, but I'm just showing it to you right now. This is what they are. This is the cosine sum and difference identity and the sine sum and difference identity. Current version of our textbook uses the letters U and V instead of A and B, but I find a lot of students' writing, and my writing for that matter, is often too sloppy. The U and the V looks too similar, so I like capital A and capital B better. All right, let's discuss a couple things about these identities before we get into some examples. Let's look at the cosine one first. And the first thing you may notice is that there's a symbol here that you may or may not be accustomed to. Even if you've never seen it before, you could probably figure it out, but let's just make sure we all understand that that is, unlike the plus or minus symbol, that is the minus or plus symbol. And this is just a way of cramming two formulas into one. Here's what it means. It means that if I have a plus sign over here on the left, cosine of A plus B, it means that there's a minus sign over here on the right. And likewise, if I were to just swap those two, if I have a minus on the left, it means that there's a plus over here on the right. Okay? So again, two formulas in one. On the sign of a sum or difference formula, the second one here, you notice that those are both plus or minus. The sign does not switch. So I'm either going to have a plus and a plus, or I'll have a minus and a minus. The sign will be the same. Now, if you're wondering, do I need to memorize this? Mr. White acknowledges it doesn't have to make sense. Well, because I'm not going to make the claim that this just should be obvious, I will actually provide this formula to you on a test. I won't provide the fundamental identities on the previous page, but this one, I would feel like you're just memorizing it. I'm not interested in that. So I will provide these formulas. You just need to know how to use it. So let's look at an example on how to use these formulas. All right, we're going to find that with the sum and difference identities, we can find some more sines and cosines and tangents of angles that are technically not special. So if you're looking at that 195 degrees and thinking, oh, to the m to the g, am I supposed to know that one? No, you're not. That is not considered a special angle. And that's what the sum and difference identities will help us discover. So let me bring up something that, please don't sit there and copy this down. Please just look at this and go, yeah, I got that. This is just a quick visual of all the special angles that you should know on the xy plane. And the idea of the sum and difference identity is that we want to look at that 195 degrees and ask which two angles on this, which two special angles have a sum equal to 195 degrees or a difference. I'll mention there are multiple possibilities. So the first one that pops out to me is sine of 150 degrees plus 45 degrees. That's the same thing as sine of 195 degrees, right? So here, this special angle and this special angle add up to 195 degrees. I should point out there are more. I could use any of these possibilities. Notice that 135 degrees and 60 degrees also add up to 195 degrees. Or I could take the difference of 225 degrees and 30 degrees, 240 degrees, 45 degrees. Take the difference of those two, and so on. There are actually a few more on here. But it doesn't really matter which one you pick. They all should give you the same answer when you use the sum and or difference identity. So let's just pick one and run with it. So let me move this off the screen. And let's just go with the first one I put up there. sine of 145 degrees plus 45 degrees. So that's the same thing as our original problem statement. And since we're dealing with sine, we will look at the sine sum or difference formula. And since we are looking at a sum here, since we are looking at 150 degrees plus 45 degrees, that's what tells us that we want a plus sign both here and here. Okay, so this is how this formula works. I will say that the sine of 150 degrees plus 45 degrees is equal to, according to this formula, sine of 150 degrees cosine of 45 degrees plus cosine of 150 degrees sine of 45 degrees. And the idea is that even though this is kind of bigger and uglier than what we started with, these are all special angles. And with our unit circle knowledge, I should know how to do these. So I'm not going to take a lot of time from here. You should be following along pretty quickly and going, yes, I got this. Sine of 150 degrees, you should know that that's 1/2. Cosine of 45 degrees, I am usually inclined to put 1 over root 2. But I'm already looking ahead and looking at the denominator I'm going to end up with, and I have a preference for doing the root 2 over 2 version of that. I just like having the rational denominator in this case. So, plus cosine of 150 degrees. I should recall that's in the second quadrant, and it's cosine, so it's going to be negative root 3 over 2. And the sine of 45 degrees, same reasoning as before, root 2 over 2. So at this point, let's just simplify that expression. 1 times root 2 gives me root 2 over 2 times 2, that gives me 4. And notice that when you use these sum and difference identities, you'll pretty typically end up with a common denominator. So I'm just going to extend this fraction bar. And look at the numerators over here in the second term. Negative root 3, positive root 2. That gives me a minus root 6. And guess what, ladies and gentlemen? That's all there is to it. That's my final answer. If you're thinking, hey, that's not too bad, well, good. I hope not. And again, I encourage you to look at one of the other combinations, one of the other options we could have tried, and just verify for yourself that we get the same answer no matter which one we do. I'll also point out that this is where I would highly encourage you to just verify via calculator. That is one use where I'd highly encourage students to pick up your little electronic gizmo and just verify that we did everything on paper correctly. Okay, let's look at another example. Now I'm going to go a little bit more quickly. I'm going to gloss over some of the parts of the second example, and I'm really just going to hit sort of the high points that I was not able to make in the previous example. So first thing you notice that this involves radians. And just as you're starting to fall in love with radians and recognize their superiority to degrees, this is the one case in the year where I will say, let's just convert to degrees because they're easier to work with. Can't believe I'm saying that, but it's true. So if we do if we remind ourselves that pi is just equal to 180 degrees, and let's see, 180 degrees divided by 12, that's going to be 15 times 17, that's going to be 255. You're all right there with me, weren't you? Doing that mental math. So that was 255 degrees. One way or another, you better come to that same conclusion that this is, in degrees, is 255 degrees. And again, this is the one time in the year where I'll say, let's take radian, convert them to degrees because it's easier. The reason I say that is because when you bring all your special angles, or when you just consider all your special angles, if these were in radian, they have all these different denominators. You've got things like pi over 4 and pi over 6 and pi over 3. And dealing with all those different denominators and trying to make them common denominator can be a pain. So that's why I say let's just convert to degrees. And I ask you, look at the options here. Where do you see two angles that either add or subtract to 255 degrees? Well, again, there are numerous possibilities, but the one I'm going to go with is the 210 and 45 degrees. But again, I insist you can use any of the other options that either add or subtract to 255 degrees. Now, the other thing you may be thinking is, well, we don't have a tangent sum and difference formula. Well, hopefully you can think of what other tools we have to address that. Okay, so here's where I'm going to gloss over some of it a little quickly. So the 210 degrees, 45 degrees gives us one possibility. And I'll say, let's bust out our quotient identity, which tells us that sine over cosine equals tangent. And looking at those two, I'll just use the appropriate sine and cosine identities. And even though that looks a little bit scary, your comfort with the unit circle will come in handy here. Obviously, pause this video as necessary if you feel like it's just becoming overwhelming. I put my expressions in there, and here's the point where I'm going to slow down a bit and say, notice that this term appears in every single term in this fraction. And here's where I really need to insist that you ask questions if you're unsure on how to handle the fractions. This is the part where I see a lot of students getting lost. You need to be able to handle your fractions well enough to see this next step. To see that if and in this case, you know what, I could have just canceled those out. That's kind of where I was going, but then I look at what I had pre-written there, and it looks like what I did instead is I really just said these denominators here are present in every single term, and therefore they can all cancel out. And then what you're left with is negative root 2, negative root 6, negative root 6, and then minus minus positive root 2. That gives us what we have here, and rather than have all those negatives, I'll just multiply every single term by a -1 and get this. Now, when I type that into the calculator, I want you to notice what we get. When I type that in the calculator, just to see if we did this correctly, yeah, it works, but this is where if you're really slick, you'll notice those numbers should look kind of familiar. If this were 1 right here, would this number look more familiar? Hopefully, some of you are going, yeah, that looks kind of like the square root of 3, doesn't it? If you're really slick, you can take this, which for now, in this video, I'm going to say is our final answer. But if you're really slick and you think back to your Algebra 1 and Algebra 2 skills, you should be able to prove that that is equal to just root 3 plus 2. But we'll probably just discuss that a little bit more in class. So don't feel overly burdened by that little nuance at this point. All right, last example is one that should be easy. And I don't want you to feel bad if you have to ask questions on it, but I say it should be easy simply to say that this is one you definitely want to ask questions on. Because once this clicks for you, you're going to go, oh yeah, that's easy points right there. This one, the only little trick to it is that sometimes this should, right off the bat, look like one of those sum or difference identities, but sometimes it's slightly disguised. And here's what I mean. If we're wondering which of these two formulas does this look more similar to, at first glance, you may see that it leads off with the sign, and you may think, oh, that looks kind of like this formula down here. It leads off with the sign. But notice that that sign is grouped with another sign, and this cosine is being multiplied by another cosine. That does not fit the mold of this one. So let's discard this. And notice that it's really a variation of this cosine sum and difference formula. And here's how I would handle this. I'm going to rewrite this. I'm just going to write it up here and pause as necessary and just make sure you agree with this. I want to rewrite this in a way that looks more like our formula. So if I write it in this order, and I've got, notice that the parentheses that I've got here. And another thing I want to point out is that unlike the previous problems, we're not claiming that this is going to be a special angle. I guess I should have paused and read the directions here. We're just asked to write the following expression as the sine or cosine of an angle. We're not asked to evaluate the sine or cosine of that angle. We're just asked to simplify this down to either sine or cosine of some angle. Well, look at what we got here. In the A and B position, I have 2 pi over 5 and pi over 9 respectively. Again, I've got A and B over here, and that's where 2 pi over 5 and pi over 9 are. Notice I've got the minus plus symbol next, followed by sine of A and sine of B, and I've got those same A and B values. So that means I can rewrite that as, if I look on the left side, I could say, oh, that's just cosine of A plus B. Notice that since I have a minus right here, that means I have a plus on the other side. That's what these symbols were telling us. So that means I have, let's see, cosine of A plus the sign switches, pi over 9. Now, what about this minus on the outside? That comes along for the ride, and that's how I will handle this. The last thing I want to do, and I do insist on this when you take a test, is please don't just leave it like that. Do your common denominator thing. And let's do 9 over 9 and 5 over 5, and 2 pi times 9 would give me 18 pi, plus another 5 pi, that would give me 23 pi. The denominator is now 9 times 5 for both of these expressions, so that's 45. And again, we have a negative cosine here. So that would be our final answer there. For those who are really slick and interested in a challenge, I'll ask you to consider why, oops, let me get that out of the way, why this is also a possible solution. So again, if you're up for a challenge, see if you can determine why is the negative cosine of 23 pi over 45 equal to positive cosine of 22 pi over 45. But that's not your primary concern right now. Don't worry about that if you get a little bit lost there. But I just want to verify again that you put that all in a calculator and verify that you get the same thing. And if you had done the 22 pi over 45 thing, again, same thing. Okay? So time for you to give it a shot. As far as, if you're wondering, is that really all that these trig identities do? Is there something a little more useful that it does? Yes, this will lead to more useful things, but we'll wait for class to get into that. The purpose of these identities is not simply to just get us a few more trig values without a calculator. All right, here are your 4 to try. I'd say even if you're feeling a little bit lazy, at least do, how about this one and this one, if you're willing to only do 2. But certainly practice all 4 if you like. Pause the video at this point. Okay, I'm going to put the answers up here pretty quickly, and if you have any questions on any of them, please come on by office hours. There's the verifications for the first 2 via calculator. For C, that is what we should have gotten, and again, a verification via calculator shows that that is the same thing as the original problem. And finally, for the very last one, D, again, for those that want to challenge, I'd say if you got negative cosine 7 degrees, that's perfectly fine, but see if you can figure out visually why that's the same thing as cosine of 173 degrees. Here's the verification with the calculator.